We are going to look at a new notation, a convention this week. It is called the Navier-Hartenberg notation. In this notation, we are going to see how the links are described, how the frames are attached, and how the matrix equation for the forward kinematics are systematically written. Now, you remember this kinematic chain, and each link is attached to the previous link by a joint, and we are now going to see how we describe these links, how we actually attach frames to these joints, starting from the end joint to the base joint, and then how do we do it with minimum number of parameters, and how then do we relate the end effector, in other words, the rest frame to the base frame. Of course, to relate the rest frame to the first or base frame, we are going through relating the end frame to the n-1 frame, and so on. And then we are multiplying these relation matrices with each other to obtain the overall transfer or transformation matrix. Now, in the previous week, we looked also how to take the inverse of this transformation matrix. Okay, so we said we are going to look at how the links are described. Now here you see a generalized link. This can be a link I-1 or ith link. I-1 link is going to be here, and ith link is going to be here, and these are the joints. This is a generalized representation. Now, how do we represent the ring? How do we describe ring? There are two parameters which are important. The first one is the link length. How long is my link? The second one is the link twist. How much is the link twisting? How do we measure these? Now we have two x's here, x is I-1 and x is I. The x's are where my z x's are going to be in my xyz plane, or xyz coordinate system. These x's are where the z x's are going to be. Now look how we determine the link length. Link length is determined by this parameter ai-1. The parameter takes its index from the former joint. Likewise, the twist angle also takes its index from the former. So if there are two joints, I-1 and I, the link length, which is joining these two joints, is shown by the parameter ai-1. And the link twist is shown by the parameter alpha I minus 1. So these two parameters are enough to describe the link. Okay? Now, look at this AI minus 1. AI minus 1 is found by the mutual normal to these two x's. If these two x's are not parallel, then there is only going to be only one mutual normal or mutual perpendicular line, or a line which is perpendicular to both of the x's. If they are parallel, there will be infinitely many, but the length is going to be the same. Therefore, length is always fixed, whether the x's are parallel or not. Because in the cases where the x's are not parallel, there is only one parameter, or there is only one mutual perpendicular, and it is length determines the length of the link. If they are parallel, there will be infinitely many normals, but there will be only one length. So in both cases, the A parameter determines the length of the link. How is the twist angle measured? Twist angle, if I carry this axis all the way here so that it's going to be coinciding with this white line here, so it's going to cross the previous axis, the angle in between is going to be the twist angle. So by these two parameters, I can describe the link. So what did I do? For intersecting the links, I actually projected the ith axis all the way to I minus 1th axis so that they intersect each other, and the angle in between is the twist angle. So I show it by alpha. Okay, what is this arrow showing? This arrow is showing the direction towards which I should move so that I will reach the end effector. If the end effector is in this direction, so I should follow this arrow. If it is in the reverse direction, I should follow the dotted arrow. And this shows this also determines the sign of the twist angle, because you always use the right angle. So if you are going to follow this arrow, your thumb should be aligned with this direction, and your right hands should be closed. Your right hand fingers should be closed from axis I upon I minus 1. So you are going to measure the angle then in this direction. Okay, in this slide, you see two more parameters. These are the parameters d and theta. What do these parameters show? Now, it does not, in most general cases, the link here does not have to be on the line mutual perpendicular AI minus 1. It may be somewhere which is displaced by an amount d. How do we measure d? D is measured by the intersection of the next, so AI minus 1 But if I have another joint here, then I will have AI. Where does AI intersect axis I? So, of course, AI is, what is AI? AI is the mutual perpendicular between axis I and axis I plus 1. I plus 1 is not shown here, but when I see the AI, I understand there is another axis here, which is I plus 1. So the mutual perpendicular between these two, let's say, is joining axis I at this point. And this distance between is shown by D. And here you see there is another angle, which is theta. How much this AI twisted with respect to the previous A, which is AI minus 1, is shown by this theta angle. So the first two parameters, AI minus 1 and alpha I minus 1, were describing the link. These two parameters are describing the link connection. Now, if this was a prismatic joint, I would have a D, a non-zero D, but then 0 theta. If it were the volute joint, I would have a non-zero theta and 0 D. I'm going to explain these to you further. And today, at the end of the third lecture, I presume that these are going to be clearer to you when we actually try to solve some problems. But these concepts, since you are learning a new language, new way of representation in this course, like any language, these concepts require a lot of review, repetition. Therefore, it's not only sufficient to listen to the lectures, but you should repeat the lectures. That's why I am uploading the lecture videos. You should review the lecture videos so that these material which you are seeing the first time are going to be registered in your brain. Now let us look at the first and last links. These first and last links require special attention. Now here we summarize what we have been stating so far. I have got three axes here. This is I plus 1, and this then is going to be I plus 2. What are we doing? We are finding the mutual normals. These mutual normals are actually showing us the lengths of the links. And this one is showing to us how much each link is twisted with respect to the previous. Former week, we looked at the planar robot, for instance. All the z-axes were coming out of the paper, so they were parallel to each other. In such cases, alpha is going to be 0. And in many examples, alpha is going to be 0 because these axes are all parallel to each other. But since we are looking at the more general case, there may be twists. And these twists are shown by the alpha angles. Therefore, in describing the links, we need to specify what these parameters are. There is also a convention that the first one, for instance, if this was our first axis and this was being connected to the base, this is going to be established on the base so that the A0 is going to be 0. Remember that we establish the first frames upon the base frame. If you remember the examples we did, the first frame is always established so that A0 is equal to 0. Also, in the first frame, we establish the axis alongside the base axis, so that makes the alpha 0. This is the convention. This is also true for the last frame. These conventions are selected to make the representation of robot easy and standard, so everybody is going to have the similar type of representation of the robot. Also, what we are after is minimizing the number of parameters we are going to use in robot. Because I have been repeatedly saying to you that robots can be very, very complicated and they may involve too many parameters. Okay, we are trying to minimize them, and you will see that these 4 parameters are going to be enough efficiently present the robot's mathematics. In the first link, we put the first axis so that it's going to coincide with the 0 axis, so that there is not going to be any distance between these two. A0 is going to be 0, and there is not going to be any twist, so alpha 0 also going to be 0. This is the convention. We will follow a similar convention for the end effector frame as well. If this is the end frame, sometimes I may have an n plus 1 frame also. Here also we will have the similar convention. In other words, an is going to be also 0. So n plus 1 axis should come and coincide with the end axis. So an is going to be 0. And there should not be any twist in between. So alpha n is also going to be 0. I am not putting down the rules. These are like the grammar rules, but grammar rules are not enough to speak the language. You can speak the language only when you make some examples. And so these grammar rules, let's put them aside. Let us establish the rules, but then you will learn how to apply them when we in fact solve some examples. In short, first and last links, we are going to set the constant parameters to 0. What do we mean by the constant parameters? If I have a revolute joint, I said that theta is not going to be constant because of the rotation, theta is going to be changing, but d is going to be constant because d is only existent for the case of translational or prismatic joints, so I am going to set it to 0. Or if it is a prismatic joint, then there's not going to be any rotation, so theta is not going to be varying, so it's going to be a constant parameter. Also, I am going to set it to 0. So following the joint type, either d or theta is going to be 0. They cannot be non-zero together, or they cannot be 0 together either. If they are 0 together, that means there is no joint. If they are both non-zero, that means it should be a joint which behaves both like a prismatic joint and a revolute joint, and such joints do not exist. So that means there is something wrong and we must correct this. Therefore, I will always write that either d or theta is equal to 0. Okay, it can be the first or the last link, but either one of them should be 0. So I have talked about 4 parameters so far. Alpha is the twist angle between the axes. A is the length of the link. D is the displacement between the origins of two consecutive axes, and theta is the twist of the next link with respect to the previous link. Only one of these is going to be variable. So for any link, so I'm writing this for any link. For any link, 3 of them are going to be fixed and only one of them is going to be variable. Which ones are going to be fixed? First of all, AI is going to be fixed because it comes from the structure, and alpha is also going to be fixed. Again, it comes from the structure of the robot. So either one of them is also fixed because either one of them should be 0. When they are 0, that means there is whichever one is 0, that means. So in short, we have established 4 parameters, and these parameters are called Denavit-Hartar parameters, or in short, DH parameters. So any link of any robot can be described by 4 parameters. Remember that at the beginning we had too many parameters. We needed to have at least 3 angular parameters and 3 displacement parameters. But because of the conventions we follow, and thanks to the work of Denavit-Hartenberg, the number of parameters are decreased down to 4, and 3 of them are fixed. Only one. For each link, only one of these parameters are varying. If the links are joined by a revolute joint, D is also fixed. So these 3 are going to be fixed. Only theta is going to be variable. If the links are joined by a prismatic link, these alpha, A, and theta are going to be fixed, and only D is going to be variable. So I will always have 3 fixed link parameters and 1 joint variable, theta for revolute joint, D for prismatic joint. And to summarize, alpha and AI, these 2, describe the link, and D and theta describe how 2 links are connected. How 2 links are connected? They are connected by a joint. If the joint is the joint a prismatic joint or a revolute joint, these 2 parameters determine. If I have 4 parameters with a 0 here, can you tell me what the joint is? Yes, you can, because then it must be a prismatic joint. If there are these 4 parameters, this one, these, if D is 0, then you can tell me that the 2 links are joined by a revolute joint. Okay, so these 4 parameters, the first 2 describe the link, and the next 2 describe how 2 links are connected. Now, at the very beginning, when I started this lecture, I said x's are where the z-axes are going to be when I establish the coordinate frames. So z's are established. Look, there is an important property of z's. Z's are where the action takes place. If it is a rotation, then the rotation takes place about the z-axis. If it is a displacement, then the displacement takes place along the z-axis. So z-axis is where the action is. If I establish the z-axis, then comes the question, how should I establish the x-axis? Now the x-axis are established so that they will be along the A's. In other words, along the links. Okay, so if 2 of them are fixed, then the y is fixed, because by the right hand rule, when x is closed upon y, the thumb should show the z. Okay, so if x's are shown like this in the blackboard, so this simulates the blackboard, then now answer the question, should the y-axis be inside the blackboard or outside?
I suggest you to stop the video and try to answer this.
It should be inside, because x cross y, if I close my fingers along the x and upon y, my thumb should show z. So the y-axis are in both cases towards inside the blackboard.